What do you
We
feel,
have
sir?
2 sessions with Sir. So don't miss this chance to
Hmm.
learn from one of the brightest minds in the fields of AI and
Next
ML.
slide. Next slide.
Sir, over to
Hmm.
you, sir. So you
Okay,
can
okay,
start your presentation.
okay. Hello, audience. Thank you very much for your participation in this very interesting ATAL program organized by, my colleagues and students. Anuradha Shah and Pratyusha Roksit. Both are my favorite students. They did their PhD under my guidance. As you see, they are very young and they have joined recently. Pratyusha has joined approximately 6 years before to Jadavpur University, and Anuradha has joined approximately, I think, 14, 12 years. Okay, 12 years. Am I correct, or 14 years?
14
Anuradha,
years, almost, sir.
14 years. Right now, but they have done wonderful, research in different areas of artificial intelligence. With their research and my other students' research outcome, we have actually developed the presentation today, today's presentation on two topics, one on emotion recognition that I'll be presenting right now, and also in the second slot, I'll be presenting on brain-computer interfacing. So students and they're my colleagues. I call you students by mistake, because of experience of so senior faculty, around I have experience of around 40 years, in teaching at Jadavpur University. So by mistake, sometimes I call you students, but you are all my colleagues and friends at different institutes. Okay, so pardon me, for my mistake. So let's start our journey. Today I will be presenting the topic right now on emotion recognition and control using classical and type 2 fuzzy sets. This work was carried out in Artificial Intelligence Laboratory of ETC Department, Jadavpur University. So the topics that we'll be covering includes defining emotions, defining type 2 fuzzy sets. And when we define emotion, we consider two types of fuzzy sets. One is classical, other is interval type 2 fuzzy sets. And then we'll be demonstrating one method of controlling emotion using fuzzy sets. And then we'll conclude the session. And that's all about four major issues of the presentation. Now, just see, here is a face. You can see there is a face of a person. Basically, she was a student. And we just define the mouth opening covering the lips and the teeth of a person. We say mouth opening of the person is 8 millimeter. So this is a crisp value, just 8 millimeter. But whenever we need to recognize emotion of a person, we need not be so precise because the mouth openings for someone may be 8 millimeter, for somebody may be 10 millimeter, for someone may be too small, and for different emotion, they might vary widely. So just in length, mouth opening is 8 millimeter does not signify any pertinent information. But if we represent this by a fuzzy set, then sometimes it carries significance because across different people, the mouth opening is small, or mouth opening is medium, or mouth opening is large, that may have some sensations of meaning with respect to person's own mouth opening for different emotions. And that's why instead of using it in crisp form or precise form of 8 millimeter, we just represent it by fuzzy set. Then question comes, what is a fuzzy set? Here suppose we define a fuzzy set medium. Medium means it has a value mouth opening which here is 8 millimeter, and another is you can see mu medium mouth opening, that means mouth opening being 8 millimeter. What is the membership mu of being it medium? What does it mean? Say x-axis is mouth opening as you find, and y-axis represents membership of mouth opening to be medium. Medium means it should have a peak value at the some central span. If the total span is, say, for example, say 10 millimeter of mouth opening, at the center roughly it is 5 to 6 millimeter. So it should have a peak at 6 millimeter, say for example, and the mouth opening falls on either side of 6 millimeter. Then it signifies that the mouth opening of the person is medium because at 6 millimeter, that means half the way of the center of the span of the total mouth opening, it has a peak. In case it was large, then at some value, initially mouth opening should be smaller and should gradually increase over, say, mouth opening. So as the mouth opening increases, if the membership increases gradually, and then I call it mouth opening to be large. Similarly, when the mouth opening falls off, say gradually in an exponential form, say with a maximum value 1 at mouth opening being 0, and gradually if it falls off, then we call it mouth opening to be small. So basically, we can represent the mouth opening 8 millimeter to be medium by a membership value. Just see, in the x-axis, I put mouth opening is 8 millimeter. On the y-axis, we say the mouth opening is medium to a degree of 0.4, where the maximum degree is 1. So this is a good information, because if we like to compare the mouth opening of different persons, then the x-axis scale may vary, but the membership will be close to 0.4 if the mouth opening of a person is approximately 8 to 10 millimeter, like that, because the membership curve shape will be slightly different. That's why we try to move from crease value to membership value. Now, during my presentation, if any of you have questions, you can ask me, stop me and ask questions. Now, to recognize emotion of a person, what do you do? So we have some fuzzification, just as we see in the last class, last slide. This is a fuzzifier. That means it encodes mouth opening into fuzzy membership values. Okay. So we can have fuzzifier or fuzzification process for different parameters of face, like mouth opening, maybe eye opening, and eyebrow constriction. We just convert them into fuzzy scale between 0 to 1. Now there is a line of parallel lines. That's why they can see a solid lines here. The solid arrow indicates there may be large number of output variables. Maybe mouth opening may be large, one line. Mouth opening may be moderate, another line. Mouth opening may be small, another line. So 3 lines in that sense. Similarly, for eye opening and eyebrow constriction, we can have multiple lines. That's why we have some solid and solid arrow here. Now, there is a fuzzy rule-based classifier. This actually classifies the emotion of a person based on his facial expression. Suppose for a given facial expression, if we could measure mouth opening, eye opening, and eyebrow constriction, then we can classify the person's emotion into 6 grades, maybe happy, angry, anxious, with different membership values. For example, if we find that the membership of a person to be happy is the largest, then the membership of the person to be anxious or say relaxed and other thing, will be calling the person to be happy. So we have to determine the membership of the person's emotion to be happy in that regard, and also membership of the person's emotion to other category of emotions like anger or fear or anxiety, like this. So this actually will be working out, and I will demonstrate how to compute these things. For the computations, we need to demonstrate, we need to develop some fuzzy rules, and we need to have the fuzzifiers, and the main engine is the fuzzy rule-based classifier that I will be explaining shortly. And now consider a person's mouth opening region. This is an actress, one particular actress's mouth opening part is segregated from the image, just taken out from there. Now, what we do for processing, main objective here is to determine the mouth opening of the person. To process the mouth opening, first we do the digital filtering. What is filtering here? We simply do median operation. Median means, in this case, we have a say image of 200 cross 200 pixels, for example, say, and then for each pixel typically has 8 neighbors. For example, a pixel 1 has 8 neighbors except that corner pixels. The corner pixel cannot have 8 neighbors, but remaining other pixels should have 8 neighbors. And these are, suppose, for example, some pixel intensity value in one scale. Here the pixel intensity could be in red plane, green plane, and blue plane. So there are 3 RGB image. So basically in R, G, and B plane, we have the pixel intensity varying from 0 to 255. So 0 means red minimum and 255 means red maximum, in that way. Okay. So similarly, whenever you consider dark image, then black means intensity is 0 and white means intensity is 255, because all pixel intensity are encoded in 8-bit format. 8-bit means 0 to 255 in binary. Now, suppose a particular, for any point in the image, we just do median filtering. Median filtering means, I mean, suppose the intensity values are like this, 2, 1, 3, 314 and 355. We just put them in an array, in an ascending order. and then we take the peak, we take the central value. The central value is 3, so we replace the central value 1 by this 3, and this is called median of the data points, or in this case pixel intensities. So for entire image, for every points or pixels in the image, excluding the outer boundary layers where it cannot be done in this manner, but excluding the outer boundary layers, everywhere you'll be getting such grid points, I mean 8 neighborhood grid points, and we can evaluate the, I mean, say, median of those pixel intensities between 0 to 255. Every value should be between 0 to 255 in red, green, and blue plane. So for all these three planes, we can get the medians, and then we can represent the image as a median filtered image that looks better than the original image. Just see that there are some dark patches which are eliminated mostly in the second figure because this is median filtered image. Now we need to evaluate the mouth opening. As you can observe, the mouth opening means from the teeth's upper region to teeth's lower region. That is, we can easily see. But how does the program can do this? For this, we need to do image segmentation. And the image segmentation is here carried out by using one algorithm called fuzzy C-means clustering algorithm. Now, I first show you the results of the algorithm. Just see we just automatically segregate the mouth region from the rest of the image by a process of image segmentation. My objective is to segregate the image into lip region and non-lip region. Lip region means the mouth region, and non-lip means rest of the mouth region. That means this part, rest of the face region. And then we converted it, the segregated part, automatically segregated part, that will be demonstrating in the next slide how to automatically segregate it. But right now, after segregation, what result we obtain? Just see. So the teeth region is prominent here. Then this is the shadow here. That is prominent here. And in the lower lip, some part of the lipstick is out. And that's why it looks like white in the grayscale image. So basically, we will evaluate the mouth opening, which will be this much here. The mouth opening this much. So we'll be evaluating this thing, but whole thing automatic. Now the question is, how by fuzzy C-means clustering, we automatically segregate the mouth region from the rest of the image. That is called image clustering and image segmentation. And then how will we evaluate the mouth opening? That I demonstrate in the next slide. See, to evaluate fuzzy C-means clustering algorithm, we have to initialize 2 pixels in the image. They are much more bigger pixels than they really are. This is for demonstration only. So let's consider one pixel here, which is called non-lip cluster center, and one pixel here, which is the lip cluster center. It need not be on the lip. It could be anywhere here. Now, for every pixel in the entire image of 200 cross 200 pixel points, we just consider 5 parameters. One is the red intensity R, the green intensity G, blue intensity B, and the XY coordinate of the image. If the origin is here, the X coordinate and Y coordinate of any pixel can be evaluated easily. So any pixel in the RGB image here is represented by 5 dimension red, green, blue intensity and XY pixel position. Then we need to actually cluster the centroids. We need to evaluate the centroid of the lip region and non-lip region, and evaluate the region of the lip and the non-lip region automatically. That is called fuzzy C-means clustering. Let's see how. So what do you do? First, we initialize the cluster centroid at these 2 points. That is step 1. Then for each pixel on the image, we do this thing. What is that? We identify that pixel, any pixel in the image, whether it will be a supporter of this cluster center or supporter of this cluster center. The question is, how do you evaluate? For example, let's take a point very close to here, say this point somewhat here. So the distance of xy is known, but RGB value here is also very close to the RGB value here. So effectively, what we find that any pixel which is close enough to this blue dot will have a more support to this point than this point here, which is more red because it is close enough to of the lip region. So all those pixels which are very close to the neighborhood point here and does not fall on the lip will be actually supporting this point, because the distance of those points with respect to the cluster non-lip cluster center will be much smaller, because they are very close with respect to the 5 attributes red, green, blue intensity and XY pixels. But some points which are, for example, are close to the lip region, they are similar to this point because it is more red as it is close to lip than this point, and the green and blue intensity here are less, here also are less, and the pixel intensity and the Pixel position, they are close enough to the XY coordinate here. So with respect to, again, all these points which are close enough to leap, they have a more support to this point because their distance with respect to this cluster center is small. In that way, first to evaluate for every point or every pixel in the image, how many of the pixels support this point, how many of the pixels support this point based on the distance measured. The smaller is the distance of a pixel in the image, the better is the support of that pixel to the particular cluster center. Then after we evaluate this, then if we evaluate, suppose out of 200 cross 200 pixels, majority will be supporter of this. So I will compute the centroid of those points, and it will be occupying the position of the centroid using fuzzy Siemens formula. I will be demonstrating the formula in the next slide. And those pixels which are supporter of the lip region will be supporting this point. So it will be occupying almost the centroid of the supporting points XY, RGB XY coordinates supporting centroid. So 5-dimensional centroid, and that will be positioned there. So after you obtain it for one iteration, we repeat this process from step 2. That means again, we evaluate the cluster center. I mean, we again evaluate this distance, and based on this, who are the supporters of these 2 points, and effectively based on the supporters, I mean, this point will be occupying the centroid of these supporters, and this point will be occupying to the centroid of the supporters, and these two cluster centroids gradually move over iterations. A point will come when these cluster centers will not move further because they will be occupying the centroid of the right clusters, and then we'll find this will be occupying to the lip region, and that will be somewhere else on the image. So this is called basically fuzzy Siemens clustering algorithm, which is it is similar to classical k-means clustering, but there are much more sophistication here. Maybe I won't be able to cover all these here because of time, but I just showed the formula which you evaluated, and you can get it from any standard book, even my book or any other books of computational intelligence. So this is the cluster center formula for lip region and non-lip region. And this is basically the membership evaluation formula for lip region and non-lip region. So basically in the program, what you will do, you have to initialize the membership of 5-dimensional pixels for lip and non-lip region for 2 classes. As I have shown before, initialize the cluster center and initialize their memberships. I did not say about membership previously. And then what you do, then you evaluate them. So you know the membership of each pixel to two cluster center, but sum of the membership of the each pixel, any pixel to the 2 cluster centers must be equal to 1. That is most important. That means suppose there is a point here, if the membership of that point to this cluster is 0.7, then membership of that point to this class must be 0.3, such that sum must be 1. And that has to hold for all points or pixels in the image. In that way, all pixel points of 200 cross 200 pixels are initialized, have initialized membership values such that sum of the membership of each pixel in 2 cluster, lip cluster and non-lip cluster must be equal to 1. Then we have to evaluate cluster centers by using this formula, and also you have to evaluate the membership functions of that pixel. I mean, again, using the cluster center VL, VNL computations. So in that way, we evaluate the membership of each pixel in the 2 clusters, say L and non-NL are computed. These 2 steps of computing cluster centers and membership evaluation will be repeated many, many times unless the point comes when the cluster centers VL and VNL does not change further. That means cluster centers of lip region and non-lip region do not change further, and then we stop. Once we stop, we'll be getting the lip region, and if we just lip region, if we, for example, convert it into a grayscale image by taking the average value of R, G, and V intensity at every pixel, we'll be getting a diagram something like this. So this is basically a fuzzy Siemens clustered, in cluster lip region or mouth region of the image. Now, over the mouth region, we can evaluate the mouth opening. That is one feature of emotion recognition. How to get the mouth opening? So this is basically a grayscale image, and it is converted again into a completely dark white state. That means it is thresholded. Thresholded means suppose the intensity 0 means it is close to dark, and intensity 255 means close to white. If we take a mid value, say 128, so any pixel intensity which is less than 128 is declared as dark, completely dark, so black. And any pixel intensity which is above 128 is called white. In that case, we'll be representing the image only in two level instead of grayscale image from 0 to 255. Now it has only two scales, which is 0 and 255, or above 128 and below 128. They are converted to 255 and 0 respectively. So now the intensity of the image have only two values. So it's a binary image. Only 0 means say black and only 255 means white. Now it is useful for us to evaluate the mouth opening. Please look, the mouth opening is this region. So upper teeth here, in the next slide, upper teeth here and lower teeth end here. So this is the mouth opening region. But how will you automatically determine this? For this now, we just count the black pixel count here. We start here, the black pixel counts we are plotting. So black pixel count gradually you see black pixel intensity, if we find that is high here, that black pixel intensity is reducing whenever, because here some white pixels appear. So black pixel intensity here is reduced. So this is the first minima of the black pixel intensity count here. Then again, black pixel intensity decreases. So, and some point here, again, black pixel intensity increased. But again, you see here, second time black pixel intensity, second time decreases, third time decreases. Second time it decreased here, and third time it decreased here. So between the first time and third time decrease in the black pixel intensity count, you will be evaluating basically the mouth opening. So mouth opening region is determined by the two minima of the black pixel counts. So it is very simple and straightforward to provide you the mouth opening in actual values, but you can convert it into fuzzy for your correct evaluation of emotion, because the mouth opening of a person for different emotion slightly may vary across people, across gender, across say or religion, and also across a particular person geographical location, means culture and other thing. But still, on a generic sense, if you convert into fuzzy, then it will be irrespective of culture, irrespective of say gender, and also say age and other thing. Now we need to determine another feature called eye opening from the image. So basically, in the original image, we originally have some eye say segment of the image. So not directly segment. What should I say? This is the cutout image of an eye, but it may not exactly match with the eye of a person, unknown person. For an unknown person, this eye will differ, but it's an open eye of an unknown person. Then for a given on a given image, we just search for this kind of thing. Search means basically partition a given image such that a complete eye appears in the say matrix. That means suppose entire image is partitioned, suppose say 32 cross 32 blocks, where each block may contain a complete eye. And then you just match this, I mean this eye with any other locations here. Okay, so this is basically called template matching. Instead of matching the pixel wise, we evaluate certain features of the template and then match the template of say 32 cross 32 with another block of 32 cross 32 in the image, big image. And that way, if you partition the entire image into say several blocks, you can match it and identify where this appears by template matching. In fact, we have our original algorithm for template matching, which is very fast. I mean, this was done long ago, around 25 years ago from now, in one of our old papers. If you are interested, they are also there in the reference, but you can find it there. So after we get the, I mean, say eye region segregated out from the original facial image, we have to determine the eye opening. But how to evaluate eye opening? For this, again, I count the dark pixels over the rows. Over each row, how many dark pixels? So you see, if I compute, say, vertically, for example, if I compute, say, vertically, in this way, sorry, not rows, over say each vertical line, we compute the dark pixel count. So in this region, you can get the dark pixel count to be maximum. And we also compute the white pixel count, say column wise. So column wise white pixel count is found here. If you add up, so you can find, white pixel count basically is this much and black pixel count is this much. If we add these two, white pixel count plus black pixel count total, then that is maximum in this region, and that you can find here. So over every column on the image, on the say eye image, you identify the maximum number of white pixel count plus black pixel count over every column. And the column where you get the maximum, that is the maximum eye opening for the image. Now we can determine another important feature that is called eyebrow constriction. So this is basically one important image that was done long ago, around 20 years ago from now, 25 years ago from now. It is Professor Jayashil of IISc, Indian Institute, previously say BE College, Bengal Engineering College, now IIEST, Sipur, So she is a professor of computer science, and she was my first PhD student. So basically, you can evaluate the eyebrow constriction here. Now, what happens whenever a person constricts his or her eyebrows? What will happen? There are dark and white pixels because eyebrows are constrictions means there are hills and valleys. So whenever light falls on the hills, they'll be bright. Light falls on the valley region, they'll be dark. So there'll be patches of white and dark patches. Now, and therefore, if you measure along the length of the eyebrows, if you measure the variance of pixel intensity, there will be you can find some variance. Say, and you have a threshold variance, suppose you define when the intensity value there on the intensity value variance is below the threshold. That means you compute the variance from the beginning, and the variance will decrease gradually as you go out from the region, go out from this window, outside the window. There will be more or less uniform, but within the window, the variance is large. So you have to define how far the variance is, within greater than some threshold, within which region. And accordingly, you can evaluate the length of the region, which is called length of eyebrow constriction. So on the given image of the face, first you need to identify the eyebrow region by segmentation. And then on the segmented image, and considering the window, you can evaluate the length of eyebrow constriction by identifying the pixels where actually the variance of pixel intensity is crossing above a threshold. And in that way, you can get the length of the region. Length of the region means the length of the rectangle, and that is the approximately the length of eyebrow constriction. Once you get all of this, you can convert them into fuzzy memberships. So there are fuzzy membership for x, any variable x, real variable x, to be high, to be low, and to be moderate. There are standard membership functions like this, where a, b, the parameters, and x mean, and sigma, they are all standard parameters. So we must have the membership functions as we did before, like this at the beginning slide. We have something like this, a membership function looks like this. So we can have, this is for medium, or similarly, we can have say low and high similar membership functions. And once we have the membership functions like this, these are the expressions of this. And we have certain rules. What are the rules? Just look at one rule. If eye opening is moderate and mouth opening is small and eyebrow constriction is large, then the emotion is very much disgusted. So this is one idea. When a person is disgusted, his eyebrow constriction seems to be large, his mouth opening is tight because he is not happy as such, and his eye opening is moderate or small. So that way we constructed some rules from common sense reasoning. But these rules are mostly applicable in Indian context. So for most of the Indian people, you can correctly determine it, irrespective of gender and locality within the country. Now, how to evaluate the person's emotion to be angry or happy, this kind of thing? For this, I just give you a very simple method. For example, suppose this is in general, there is a rule like if x is a and y is b, then z is c, where x and y are two, say, parameters like mouth opening and eye opening, and maybe eyebrow constriction, suppose, is not given here, and z is the membership of the person for a certain emotion c, say membership of the emotion to be angry that you want to evaluate, suppose. So in this case, the measurement of mouth opening is x dash, measurement of eye opening is suppose y dash. These are x and y axis. So x dash and y dash are the measurements at these 2 points. Okay. So from the membership curve, this says membership of say eye opening, say for example, is say large. Large means initially is increasing and then saturates to 1. Maximum is 1. So this is large. In this case, membership of mouth opening is small. So initially it's small at when the mouth opening is 0 or very small, membership is high. As mouth opening increases, membership falls off gradually. And this is suppose, say person is surprised to some extent. So membership of person to be surprised, that is medium. So medium means at the center there is a peak. So what will you do for certain measurement of x dash, that is eye opening and mouth opening? What you do? Get the values, these two values. You take the minimum of the membership values. They are between 0 and 1 because membership value can be in the y-axis. They can have value between 0 to 1. And then the minimum value will be again between 0 to 1. And this membership curve has a peak which can be maximally 1. If it is 1, it is called a convex membership. It can be less than 1 even. So the minimum value, suppose it is 0.7, if the 0.7 value is below the maximum value, we take the minimum of this curve and this line, and then we'll be getting something like this. That means just this part will be clipped out like this. And this is called actually the fuzzy inference of membership of a certain emotion to be say to be surprised is medium. Medium means something like this at the center peak. It will be looking something like this. Now to get back the actual information to what is the actual information of the emotion, of the numeric value of the emotion, you can actually defuzzify the signal. The defuzzification means at every point you sample the value of z, then this z and mu z c dash, you take the product of z belonging to c dash into z and sum it up of overall z sigma over this and divided by sum of the memberships. That means basically you sample the values over z, then for each value say z equal to z1 and the membership of this at z equal to z1, take a product. Take a next sample value at z equal to z2, say for example here, and multiply that z2 with the membership value at z equal to z2. Go on doing like this up to the end. Sum them up and divide it by sum of the memberships, and sum of the membership is basically the area under the curve. So if you do that, you'll be getting the numeric value of the emotion to be surprised. If you can evaluate the numeric value of each emotion in the manner, then the emotion which has got the largest numeric value is considered to be the emotion of the person. In that way, we can recognize the emotion of a person. Now, this is some experimental thing. To actually arouse the emotions, we have different means. It could be audio visual, it could be say in any other way. Maybe you can say, for example, pinching somewhat, so giving pain input, so the emotion will change accordingly. So in this case, we have different emotion generating videos. So first one is for anxiety. The second one, as you see for disgust, it is generating disgust in the subject, and side by side for one subject, how the disgust is generated for one of our students, Madhumala, is demonstrated here. Gradually she is disgusted. Just look at the frames gradually. Then for the third case is a very interesting English movie, Fire, and you see the Fire is very serious movie, and the person is having fear for this. So the person is gradually afraid. The fourth one is a Bengali movie, very famous Bengali movie. It is for generating happiness. It is funny, basically. So the person is gradually happy as he witnesses the four stages, four samples of the movie. And last one is for sadness. It's a murder history. So effectively, person is gradually sad. So we can recognize the emotion of the person from the facial expression automatically. But we check whether for the original arousal of emotion and actual emotion aroused, whether they are same, and by machine can automatically detect the correct aroused emotion. Once the emotion is recognized, we can represent it by a confusion matrix to check to what degree they are correct. Confusion matrix means these are desired emotions and these are aroused emotions. So basically the diagonals of the matrix should have very high value in most cases, but in some cases it may not have poor values. In our case, all the diagonals have value close to 96 and above, 96% and above. But the off diagonals, they are basically false alarm signals. They may be giving wrong signals and they are generating false alarm in some cases. But in our case, false alarms are very few, so they may be ignored. So this is how you can recognize emotion of a person from facial expression. Now, once you recognize this, you see in the emotion, in the transformation of the original, say, facial information into emotion, we use the membership functions. Look at here the original expressions. These are the membership functions. But there are certain parameters, A, B, X mean, and sigma. And these parameters initially are arbitrarily chosen. As they are arbitrarily chosen, they can never give very good information. So what to do? We need to automatically adapt those values for base results. So we need to optimize this. And for optimization, what we did, suppose this is mouth opening, eye opening, and eyebrow constriction, and they are fuzzy encoder. That is fuzzy membership function generator in the three scales, large, medium, and small. Mouth opening to be large, mouth opening medium, mouth opening small, eye opening to be large, medium, small, eyebrow constriction to be large, medium, small. So it's a vector of 9 information. This vector is called f dash, and that is a relational matrix R. By multiplying this thing in some way, this is called max min composition operation, we get the emotion of the person at time t. So the question is, from feature value, we get the emotion value directly. Now and then, if we have a desired emotion vector, if the vector m is desired emotion is correctly determined, and then by say theoretically it is determined, and we take the difference of these two vectors, and then by a learning algorithm we can adapt the parameters of the fuzzy encoder, means membership functions. We have to tune it in some manner such that effectively the error here, error norm becomes zero. This error is a vector. Error norm means Euclidean norm of error. The Euclidean distance of this vector with respect to origin will be zero. But who will be the learning algorithm? You can use many algorithms. In our case, we use the gradient descent learning algorithm, which is very popular and being used in backpropagation algorithm. So this is all about how you recognize the emotion and you properly tune the parameters of the membership functions so that you claim that your emotion recognition is correct to a degree of 96% and above. Okay, remaining 4% you can nothing to do. Then either you have to take more features, not only just 3 features, and also better method of computations for correctly determining emotions. But once you recognize the emotion, you can control the emotion, and that is most important. And probably none else in the world have automatically generated some means for controlling emotion that we did long ago in 2009. This was our 2009 paper, 15 years ago from now, 16 years ago from now. And at that time, we first proposed how to actually recognize emotion from facial expression and then automatically control the emotion by rightly choosing the right amount of rightly choosing the right music and video that can actually generate the necessary amount of positive or negative stimulus so as to bring the emotion to the desired standard. And that we did long ago using some philosophical thing. What is the philosophical
Sir,
thing?
sir,
Yes,
I'm
time out.
Anurag. No, 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 sir. Sir, your screen sharing is off somehow. Sir,
Off.
kindly check. Kindly check, sir.
How it became, how long it is off? Right
No, no,
now or long before?
it is just within 1 minute or a few
1 minute
seconds, sir.
screen sharing is off.
Yes. Yes, sir, it is visible now.
Visible, ঠিক আছে. Okay.
Yes,
Yeah.
sir.
Mm.
Sir, I think we lost in the last page actually. From the
Last
last
page.
page,
Okay.
I
This
think
one.
from the last
This
page.
is
This one, sir.
this one
This
is
one, sir.
clear.
This one.
Oh,
Yes.
this
Yes.
one you could not listen. Okay. So basically, once you obtain mouth opening, eye opening, and eyebrow constriction from the actual image, and we recognize the emotion, but there may be some errors. The errors is due to the choice of the parameters A, B, M, and sigma in the expressions here, A, B, sigma, and X mean. X mean is M actually. So question is, in order to correctly get the emotion, we need to adjust the parameter. But how will you adjust it? So for mouth opening, actual precise value of mouth opening from a facial expression, you encode it in fuzzy. So mouth opening low, mouth opening medium, mouth opening large. They have 3 different membership values. Similarly, for eye opening low, medium, high, 3 membership values, and for eyebrow constriction also 3 membership values. So you have 9 membership values altogether. These 9 membership value is a feature of 9 dimension, that is f dash. And there is a relational matrix that transforms from feature to emotion. So this is a relational matrix already constructed. Then how we will be getting the emotion vector from here? And there is a desired emotion vector. We take the difference of these two vectors and get an error vector, component-wise error vector. This error vector is fed to a learning algorithm to adjust the parameters A, B, M, and sigma in a manner so that effectively the error norm will be zero. So how will you design the learning algorithm so that error norm or Euclidean norm of error becomes zero? This is basically a tricky problem. There are many ways to do this, but in our case, we use gradient descent learning algorithm, which is commonly used in backpropagation algorithm of neural network. So by that, we adjusted ABM sigma such that for a correct facial expression and the corresponding emotion vector here, the error norm becomes zero. And once we attain this, we say that this method can correctly give you the right emotion of the person from the facial expression. And then we'll be in a position to control the emotion. To control the emotion, we use one philosophical thing. This is basically done, by one humanities professor. At that time, she was student, Oruna ma'am. Yes. Can you hear? Anyway. Okay. Now suppose this is a state transition model of emotion. If a person suppose is disgusted, then if you provide him some positive instances, she or he may be sad. With more positive instance, she or may be happy, anxious. And again with more, she may be happy. If we apply negative instance, negative input. Maybe negative input means you just tell her some negative words, maybe shocking words, maybe a wrong information which negates something, maybe something actually a negative information, maybe someone has failed in the examination, you report to her that she has failed in the examination. These are negative instances. So whenever there is a negative instance at happiness, the person may be anxious. With more negative instance, the person may be sad. And again with more, whenever the person finds he or she is not responsible for this for this situation, then the person will be disgusted from sad. So this is a very basic model of emotion we collected from, humanities literature, psychology literature. Then what happens? At any time, the emotion, ith emotion, we have basic 6 emotions. Say, I have shown you only 4 because of lack of space, but there are 6 basic emotions. These are the basic 4, and that is relaxed, is one, and another is, say, angry. Angry is another. So altogether 6. Now the question is, for the ith emotion at time t plus 1 is determined from the jth emotion at time t multiplied by wij. Suppose a person is sad here. At time point t, person is sad, but in next time point person may be happy. So in that case, there will be positive instances twice. So what I mean, so basically in this model only one link, but sometimes we have multiple links from any other emotion to here. In this case, we provide a multiple link. If from sad, the person can have a transition to happy directly. So that person can have a happiness directly from anxious also. So that provisions is there in the rule. So what we did, from any emotion j, we can come to ith emotion at time t plus 1. So any emotion j at time t, we can come to ith emotion at time t plus 1 by multiplying by a scale factor wij, and this is summed up over all j, means for all emotion j, which is other than I. Then there may be the positive instance at a particular jth emotion. The positive instance is applied at the jth emotion, then this is the positive instance's strength at time t and a scale factor. And the positive instance may be applied in each of the possible input emotions j. Similarly, negative instance may be applied at the jth emotion. So this is the negative input, negative influences, and the corresponding factor. The minus sign is that we reduce the emotion. So it is scaled in the way the happiness would have a large value, anxiety less, sadness less, disgusted less. In that way, the formulation is managed. And if you represent the whole thing schematically, we can say this is the diagram of a emotion process. So what is the emotion process? So basically, we have a original, say,
Am I
yes,
audible? Hello.
yes, Anirban, yes.
Sir, in the last PPT, you showed the negative and the positive. I think that pause in and pause neg in, that is the membership function. So the values of the membership function will be determined by the user, I think. And in this case, disgust and happy, you have put negative in as a disgust. Means the highest value of negative in is disgust, and the positive in highest value is happy. Isn't correct?
Right, exactly. So now what happens, for the modeling of the emotion, then what you can do, emotion transition. So if you have a emotion, right emotion vector, say mt plus 1, then that is a delayed. It is delayed means it is mt only. So mt into wt. So w into mt will be getting by providing a delay in discrete logic z to the power minus 1. Mt plus 1 vector multiplied by z to the power minus 1 into I. That gives you i's identity matrix, gives you w. Gives you mt multiplied by w. So that is the first term. Then the positive influencing controlling matrix is B. So mu into B, that is positive influence controlling, and mu dash into C, negative influencing controlling with a minus sign. So that will be added up with mt plus 1 into delay means mt into W plus mu into B minus mu dash into C. That is basically, and scaled up after some scaling, we get MST plus 1. That is the scaled thing. And actual thing is MT plus 1. We can get MT plus 1 or scaled thing just by scaling that thing. But for normalization, we can do scaling, we'll be getting MST plus 1. So this is basically emotion dynamical model that was proposed by one of my students from humanities. I mean, she is Dr. Aruna Chakraborty, now a professor of, say one college, St. Thomas College. Now, there are certain rules for emotion control. Again, we have some rules like if error is small and error is positive, then apply positive influence of small strength to get actually happiness actually. If error is moderate and error is negative, then apply negative influence of moderate strength to bring happiness. So this is basically the emotion dynamics that you already pointed out, and this is the fuzzy controller for that. What does the fuzzy controller do? The fuzzy controller will select the right, say audio visual movie, audio visual, clips, okay, with proper strength. Each audiovisual is properly leveled with a strength value to actually add up to the current emotion, to arouse the emotion level positively or negatively. For positive, to grow positive emotions, the corresponding audiovisual with positive strength, which is normalized by 50 audience previously. They are previously actually recorded and or previously leveled by 50 audience, and they have put some numeric value there. So the emotion controller will select the right music and video and the corresponding numeric values. They are non-fuzzy numeric values. And then the corresponding music and video will be presented to the person. Okay, and there are two switches you can see. Either the positive one will be active or the negative one will be active, depending on the control logic here. Okay. So in the control logic, this is basically we have the fuzzy rules and membership computations, all those things for similar to those things as we used for emotion recognition. Now, effectively, what happens? Just see, this is one student over we experimented. This is taken from the journal paper, IEEE paper of our previous publication in 2009. So effectively, for this person, for 28 seconds, you know, I mean, certain music of 28 strength, certain music of 28 strength is actually generated for this much duration. And then the person is basically from this state, as you see, as is written here, you can see from the disgusted state, that is leftmost, the person is now effectively to a sad state here, then to anxious state here, and finally happy state. And in each case, the audiovisual is presented first time for 28 amplitude of audiovisual strain for this much duration for this transition, then for this much duration of 16 strength to convert it to transform the person's emotion from sadness, from sad to anxious, sad to anxious, and ultimately from anxious to effectively happy. So we have to apply a strength of 8 units, for this much duration. In this way, the person will be happy. So this is the first kind of representation, how to generate control commands for making emotion happy from any other states, both recognition and control using classical logic. Now, with the time left, I think we can discuss the higher order logic, basically, interval type to fuzzy logic, and if time permits, generalized type to fuzzy logic for emotion recognition control, and for other control applications that I have already heard the slide. So maybe if we can cover it up, we'll be discussing that thing. So emotion recognition using interval type to fuzzy reasoning. So let me discuss what is interval type to fuzzy reasoning, interval type to fuzzy sets, and how it differs from classical type 1 fuzzy sets. Suppose if as we in the first slide we have discussed the person's emotion, mouth opening was say medium. So this is the same thing, mouth opening to be medium, only one curve. But suppose if I take opinion of say 5 people, in this case 4 people, I have taken opinion. The 4 people have drawn 4 different membership curves with the peak shifted, looking similar but the peak shifted. The x-axis is mouth opening of the person, and it is mouth opening is say for example medium. So mouth opening medium, 4 people's opinion are different. They are just 4 people, maybe you can call them expert also in common sense reasoning. Now the question is how you integrate all the people opinion together. In classical fuzzy set, you are happy with only one such membership functions. But in interval type to fuzzy set, we need to integrate all of them. One way to integrate them just by taking union of all of this. Union means just see, follow the mouse, it will be like this, then entire one and here, just like here, as I draw by blue curve. And then the intersection of these, the intersection is this part, only this inner triangle. So inner triangle is here. So within the inner triangle and the outer triangle, you can include all the membership functions. So we can say the union of all the membership function is the called the footprint of uncertainty, FOU, footprint of uncertainty. That is the region between the upper membership function and the lower membership function. LMF for lower membership function, UMF means upper membership function, FOU is footprint of uncertainty. What does this mean? At a particular value of mouth opening, as you find, say certain value, say 6 centimeter, what you find? You may be finding 4 different membership values here. One is called U1, say this is U1, this is U2, maybe U3 and U4, 4 different membership values. Then which one will you consider? You say, I cannot consider any values because that is varied widely only for 4 people. If I have 100 people, they will vary much more widely. So what are you doing? You are taking the minimum of these memberships and maximum of these memberships. And at this line, if you plot the line, so membership will vary from minimum to maximum like this. It can take any value in this region. Similarly, anywhere, any value may appear on the vertical scale. If this is mouth opening, the membership value at any point, for example, here will vary from minimum to maximum of this much. Here, it will vary this much. And that's why it's called interval type 2 fuzzy set. Now, in this case, x-axis is mouth opening and y-axis is called mouth opening to be medium in interval type 2. There is a curl notation over this. This curly sign means it is an interval type 2 fuzzy set. Now, in interval type 2 fuzzy set, so x-axis or linguistic variable is x-axis. This is called primary membership value. Primary membership value means just in the previous slide, these are primary membership values. The y-axis is primary membership value. But when you integrate them together by taking union, you get also in the primary axis only. But what is the secondary membership? Secondary membership means at a particular linguistic value, say x equal to say 0.5 or something, mouth opening is certain. Mouth opening is say 2 millimeters, say for example here in the first grid 2 millimeter. And say for example the primary membership of mouth opening to be small is suppose this value. Say this value is say 0.4. Then what is this z value means what is the membership value of mouth opening x equal to say 2 millimeter and membership is 0.4. So this is suppose 0.4, this length. When mouth opening is 2 millimeter, means this is 2 millimeter and say membership is 0.4. So what is the membership of these two things being correct together? Then mouth opening is 2 millimeter and the membership of that to be 0.4. To what degree this together is correct? That is represented by z-axis. In interval type 2 fuzzy set, all the z values are 1. This is very, very important. All the z-axis values are 1. So basically, we can drop them out because all these z values are equal. Then what is the need to put it? But this is only represented for demonstration that the z values of interval type 2 fuzzy set must be 1. They are called secondary membership. Primary membership is u-axis. The x is the linguistic variable value and mu xu is the secondary membership, which for interval type 2 fuzzy set are all lines all equal to 1. But if you move to general type 2 fuzzy set, that will be different. This is x, linguistic variable value. This is primary membership value u, and this is mu xu. See, the membership values, they are different. Somewhere 1, somewhere 0.8. In this case, I have drawn a special case that looks like a plane like this, but need not be always like this. Here I want to represent certain thing to mean this. So it looks like a plane like this, where the membership values are variable. So here the mu xu carries certain meaning because they may have different values, somewhere 1, somewhere 8, somewhere 0.5, and that together may form some 3D surface. In this case, the 3D surface is a plane. So this is general type 2 fuzzy set and geometric representation of general type 2 fuzzy sets. So I believe this is clear. In interval type 2, z values are 1. In general type 2, they may vary. Now, how will you recognize type 2? How will you recognize emotion using type 2 fuzzy sets? That I discussed briefly. Okay. So here, for emotion sensitive facial expression, we have to determine, certain emotion sensitive facial expressions of n subjects you are considering. Suppose n equal to, for example, say 10 subjects at minimum, 10 people's emotion. and m instances. For each of them, suppose you are taking, say, 5, m equal to 5 instances. And for k emotions, for each instance, means for each instance k emotions. That means for example, I can say for emotion anger, I have taken 5 instances. For emotion, say happy, I am taking 5 instances and 10 people. So 10 people, 5 emotions, k equal to 5. And for each instance, again 5 instance, each emotion 5 instances. So 5 5s are 25 cross 10, a small database of 250 that we created. I believe you understand. A person's each emotion, suppose 5 emotions we consider. So k equal to 1 to 5. M instances for each emotion, I am taking 5 instance. My that is for happiness, 5 photographs of the same person. And for n such subject, say small database, n equal to 10 subjects. So 5 into 5 into 10 means 250 total altogether. That is a database you created, small database for experiments. Now, from this database, you have to define a fuzzy space in the MKN space. How you determine the fuzzy space? You have some type 2 fuzzy rules and the emotion sensitive facial database. From this, you will be generating some instantaneous space, fuzzy space, and then for unknown image using the fuzzy space, you can get the emotion. So this looks like something, something strange, but actually, how do you get it? We just illustrate, and then I believe you will understand it clearly. Now again go back. Suppose this is a particular person's face. We have taken certain features. Left eye opening here represented by EOL. EOL means basically eyelid, lower eyelid, lower eyeball region to upper eyelid, upper region as you find EOL. Left eye opening. This is left eye opening. Similarly, right eye opening. So distance between lower eyelid to the eyebrow of the left eye. So all parameters here are defined. Say, for example, LEFL, just see from here to this much, upper eyebrow, so up to this much, it is called LEFL. In that way, all parameters are formally defined here. If Anuradha ma'am and Pratyusha ma'am shares this video with you, I think then probably you can see it in detail. If I explain in that way, it will take lot many hours and we cannot finish in time. So please see it later. So that means what I wanted to convey, that each feature is properly defined on the image. And we consider now 5 features for interval type 2 fuzzy logic based emotion recognition. Previously, we considered 3 features for classical fuzzy set, because that paper was published in 2009 and this was published in 2013. Okay. Now consider, say, how will you represent interval type 2 fuzzy set I just discussed. Say this is a person's emotion when she is acting. This is another student who is also your speaker, in this presentation. Now you have taken 4 of our facial expressions, during acting. And what it means, you can measure the left eye opening. Left eye opening in our case is 10 millimeters, 10 pixels. Here it is 12 pixels, say 8 pixels, and say 12 pixels. So what you do, suppose you take the average of this. The average will be coming 10.5. Then you can say membership of the left eye opening close to the center value, that you can evaluate by taking first is variance, and variance, and then standard deviation, and also you compute their mean, and you can consider a Gaussian membership function. The Gaussian membership has a peak at the center with mean equal to 10.5, and the standard deviation of this you can evaluate, and from that you can evaluate the standard Gaussian expression. All of you know, I do not point out here, and you can draw the membership function. So that represents membership of the person's left eye opening close to the center value of 10.5 pixels. Now, suppose you consider a happy person's face. I mean, again, this is Pratyusha ma'am, who will be another speaker and coordinator of the program. This was an early photograph taken in 2012 when the paper was published in 2013 in IEEE transaction. Previous was on 2009 in the same IEEE transaction. This is another student, now no longer exists. She was an MTech student, does not exist in Jadavpur, but she is a professor in another institute in United States. And they both are happy image that you can find. They are actually they are given happy stimulus, so both of them are happy, and the emotion changes. Now for Pratyusha's image, if you evaluate mouth opening, and also mouth opening, and also the mouth opening mean value and variance, and draw the Gaussian, this is hand drawn, so not proper. So maybe for Pratyusha you'll be getting like this, and for Deepti suppose you'll be getting like this. So for both of them, considering the variation to be Gaussian. and with the mean value center of mouth opening, and the variance is there by taking the variance of the mouth opening of the four figures. Then if you want to construct a interval type to fuzzy set out of this, you take the minimum of these two, the minimum is this curve, and the maximum is the union that looks like this one, then following this. So that will be like this. And the region between these two, this region is called, footprint of uncertainty. The space between the two curve, the dark curve and the pink color curve between these two, the gray color curve and pink color curve between these two, the region is called footprint of uncertainty. This is called lower membership function, and the pink color is upper membership function. So in this way, you can get upper and lower membership functions for only 2% facial expression. Each person's facial expression is represented for happiness is denoted by single curve. Okay, so if you have a happiness expression of 10 people, then you have 10 such membership curve, and I show it here. This is happiness expression of 10 people, and 10 people's opinion are averaged as if. So what you find, you get 10 such curve, and you then take the maximum of the curves as you find, as you did the took the maximum of them, maximum of these two, and the minimum of these two as you did. Similarly, if you take maximum of these curves of 10 people and the minimum of the curves, minimum of the 10 curves, you will be getting these two things. So this will be upper membership function, this will be lower membership function, and this space in between is called footprint of uncertainty. So this is for happiness, emotion, happiness, for mouth opening feature. With respect to x-axis is mouth opening, and this is for happiness. This is x-axis is say, again, this is also for happiness, and this is for left eye opening, and this is also for happiness for right eye opening. So for with respect to each feature, the x-axis value, mouth opening, left eye opening is x-axis, and right eye opening x-axis. For this, you got the membership curves, and you take the maximum of them and minimum of them, and you'll be getting upper and lower membership functions for each curve. For each curve, not shown only for one curve demonstrated, otherwise they will be hazy and does not look nice. Similarly, for anger emotion, for the three features, mouth opening, left eye opening, right eye opening, I demonstrate all the 10 people's curve, and we get the maximum and minimum in the same manner to obtain upper membership function and lower membership function for all the curves. So for 5 emotions, and actually I have shown 3, but we have taken 5 features, we will be having a matrix of 5 cross 5 looking like this. Then how do we evaluate from this? That is most important. After we evaluate this, we get a fuzzy emotion space that I was saying in previous diagram here. We get a fuzzy emotion space in this manner. This is the emotion space, fuzzy face space. And using the fuzzy space, we can recognize the emotion. So now this part, the training part is over, where you got the fuzzy face space. And now for an unknown emotion, I will recognize the emotion using the fuzzy face space. But how, that I will be demonstrating right now. So here just see, given all this, now I have a rule. If feature 1 is close to the center of the span of membership function 1, and so on, feature n is close to, here in feature n is feature 5, is close to the center of the span of membership function 5, then class equal to emotion I. So to understand this, just see what we did. This is an unknown facial image. This is also, our student Anisha, who is now a faculty of radio physics and electronics, in Calcutta University. Now, suppose this is 5 features here. I have shown here only 3 features for space, mouth opening, left eye opening, right eye opening, but I told you we have taken 5 features. So these are the 5 features here. Okay. And then for 5 features for emotion, anger, we are getting maxima and minima here. I do not show maxima, minima. But suppose these are the measurements of left eye opening, right eye opening, and the corresponding features. These vertical lines, they are the measurement values. And this cards the lower membership function here, which is 0.3, and the upper membership value here, which is 0.91. For the second curve, for the feature EOR, right eye opening, the lower membership curve measurement is 0.15 and the upper is 0.72. In that way, for every vertical line, the measurement, we get the lower and the upper membership values marked over there. Then what we do? Then for emotion, anger, we take the T norm, means the minimum of the lower membership functions, minimum of 0.3, 0.15, 0.12, 0.02, and 0.05. We take the minimum means T norm, and we got the minimum is 0.05. What does the minimum indicate? Minimum means AND operation. That means the joint occurrence of eye opening to be low to a degree of 0.3, eye opening right to be low to a degree of say 0.15 and so on. So the joint occurrence membership is 0.05. That is the AND operation of the lower bounds of all. Similarly, AND operations of the upper bounds of the all represent what is the highest degree that the eye opening left happens. That is 0.91, here 0.72, and their joint occurrence minimum is 0.68. Now we take the average of this, and this is called average of the interval, represents 0.365. That means the person's emotion is happy is true to a degree of 0.365. Okay, now we can evaluate the emotion of the same facial expression. For the same facial expression, evaluate the emotion in the same manner for other cases, means happiness, fear, and other thing. And if we do it for all the 5 emotions, we got these values. We just see for anger, we got it 0.365. For fear, we got 0.32. For happiness, we got 0.95. So we'll be saying the emotion is happy. So this is basically how we can recognize emotion from facial expression using interval type 2 fuzzy set. Now, next thing is we did it also for general type 2 fuzzy set, but this will be too complex and we cannot finish it in time. So I do not discuss it right now because this is too much complex and I mean, it requires another half an hour. So I just drop it out and I just discuss something else actually. I mean, that is how we can use, I mean, say type 2 fuzzy logic, interval type 2 fuzzy logic for other interesting control application. For this, no, people who are in, since it is a control kind of program, I just demonstrated in for another problem which was done by one of my PhD students, previously PhD student, now a faculty, I mean, and actually he worked on type 2 fuzzy control, and I demonstrate one of its interesting thing, although not emotion, but only a few minutes left. So we can briefly outline how type 2 fuzzy control can be applied to a cyber physical system. Basically, in our case, we consider a model of an inverted pendulum. Suppose that in an inverted pendulum and there is a cart, you can apply a force to the cart and the cart will move. As the cart moves forward in this direction, the pendulum, inverted pendulum will move in the opposite direction. As the cart moves horizontally forward, the inverted pendulum turns back. As the cart is pulled back, inverted pendulum will fall. So the direction will be opposite. So there is a dynamics for the inverted pendulum. And if we just represent the dynamics, and then we can construct some fuzzy rules for this. What are these? The control policy here is the angle theta t to be close enough to 0. That means, is it possible to apply some force Ft to the cart all the time so that the pendulum will be close enough to 0 degree with the vertical? That means theta t will be close enough to 0. That is the control policy. And in order to do so, what is the torque to be applied to the pendulum, or how much torque is generated to the pendulum automatically when we apply a force Ft, which may be pulling force, pulling means towards this, or a pushing force. For either kind of force, what will be the torque generated so that the pendulum always will be aligned with the vertical direction with the smallest possible angle close to 0 degree. That is the problem. That is control objective. Now, and for doing so, first we have to develop some knowledge base. If theta 1 means the angle is n means a negative, and theta 2 kt is the derivative of the error. If that is positive, then control signal, which is the torque, is near 0. So in that way, we prepared some fuzzy rules. Theta kt is angle with vertical, and theta 2 kt is the derivative of that, not error. Theta 1 kt is the angle with the vertical, and theta 2 kt is the time derivative of theta 1 kt. So we prepare 8 rules. This is very standard rules taken from literature. Then what do you do? Then suppose you have some measurements of theta 1 kt here, theta 2 kt here. And these are interval type 2 fuzzy sets. See, this is the footprint of uncertainty. This is upper membership function. This is lower membership function. And the shade represents the footprint of uncertainty. Similarly, it is another footprint of uncertainty for this case. And the upper and lower membership function. Suppose there are theta 1 kt and theta 2 kt as two x-axis. And the measurement points is here minus 1.5 for theta 1 kt and minus 3 for theta 2 kt. Then for this, no, suppose we consider it at hits at this vertical line hits at the lower membership function at this point and upper here. And here the measurement point hits the lower membership function here and upper there. We take the minimum of the lower membership functions, these two minimum, and that is called alpha 2. And we take the minimum of the upper membership functions, that is alpha 1. and this is suppose the concluding signal U1 KT or UKT, that is the control signal, and it looks like this. This is actually looking like this with the interval type 2 fuzzy set. Now we take the alpha 1 and minimum of the lower membership, minimum of the upper membership functions. With the upper membership functions and alpha 1, we take the minimum, so it will be looking like this, looking like this. And then with the lower membership function and the minima alpha 2, we take basically like this. So it will be simply like this. And if we take the, if we draw it, for one such key, it will be the shape like, it will have a shape like the shaded curve. Similarly, for a second rule to trigger with the same value of theta 1 equal to minus 1.5, theta 2 equal to minus 3, if a second rule fire, where the second rule says, if say it is negative, I mean, you want theta 1 is negative, but theta 2 is near 0. In the previous case, theta 1 is negative, theta 2 is also negative. Just see the value, both are negative. In this case, if theta 1 is negative, but theta 2 is near 0, then the control signal is negative, that kind of thing. And in that case, we get a signal like this. Result is like this. Now, if multiple rule fires, we have to take the union of these two regions, and the union is something like this. Then I have to use something called, defuzzification in interval type 2 fuzzy logic. For the defuzzification, we have to compute two things. One is called lower centroid or left endpoint centroid. Other is called the right endpoint centroid, and you need to take the average value. This left endpoint centroid and right endpoint centroid, for computation of these, there is one famous algorithm called Kerning-Mendel algorithm. Suppose just consider how to apply Kerning-Mendel in a very short time. Say this is one triangular membership function, the dark line. There was another triangular membership function. Now I want to get the left endpoint centroid. What does it mean? If I compute the centroid of this curve and centroid of this curve, they will be same because the two curves are symmetric. Centroid means, centroid with respect to y-axis. We compute centroid, okay? Because we need to compute centroid with respect of membership. So always we compute centroid with respect to y-axis, not with respect to x-axis. And then what we mean, as we did previously, for we have to actually, by Kerning-Mendel algorithm, we need to identify one point on this curve. Oh, let me stop sharing. Is it stop? Is it okay? Can you see what he
Yes,
says?
sir, it is visible, sir.
It is
Sir,
visible.
visible.
Okay,
Visible,
visible.
sir.
Okay. So basically, in Kerning-Mendel algorithm, what we need to do, we need to determine one switch point. Switch point means, I first consider moving following the upper membership function, and then fall means to a lower. This is a switch point, and then follow the lower membership curve. So basically, what I want to mean, within the membership space or within the footprint of uncertainty, I have to identify one membership function whose centroid will be the smallest. And also we need to identify one membership function whose centroid will be the largest. So Kerning and Mendel together determine those two membership functions. Question is, how will you determine those two membership functions? The idea is, if the left side is bigger, taller, then you'll be getting this left side being taller, the moment of the left side with respect to this axis will be larger. But if the right side is taller, then the moment of this membership curve with respect to the right side will be larger. So Kerning-Mendel says, first follow the upper membership function, then switch to the lower and follow this curve. But where will you switch? You can switch at multiple points. So there could be many such dark blue curves. I have shown only one, but it may switch instead of being here. It may switch from here to here. It may switch from here to here. So there are many possible switch points. Then Kerning-Mendel says, if we can identify a switch point where the centroid of this curve, by type 1 centroid of this curve, is equal to the switch point, then that switch point is needed, and that centroid of the curve is equal to the switch point. He has developed a mathematics by which he claimed, if we follow the upper membership function and then we fall to the lower membership function, there are infinite number of possible curves following the boundaries of upper and lower and switching from upper to lower like this. But then which one should we choose? They say we have to choose that one for which the centroid of the curve is equal to the switch point. Switch point means the x value. Similarly, they consider first follow the lower membership function and then switch from lower to upper and follow the upper. There are plenty of such membership function because we can switch here, you can switch later, and in so many points. You can switch even from here to this curve. So there are many possible things. So again, they say you identify a curve in like this, where the switch point of the curve, means switch point here, is equal to the centroid of the curve. If such curve can be identified, then the centroid is equal to switch point can be identified, then that curve is the possible largest centroid producing curve. This is the possible smallest centroid producing curve. So the two switch points that you obtain, they are equal to the two centroids. You take the average, and that is the defuzzification. So that is the idea of defuzzification. So by using the defuzzification, if you proceed, then CL is the left endpoint centroid, CR is the right endpoint centroid. You take the average, you get the result. But the beauty of Sumantro's work that beats even Karding and Mendel's algorithm, he has computed this entire process where Karding Mendel took a lot many iterations, around say 10 iterations, but Sumantra has done in a single iteration and much faster, and therefore his system can work in real time where Karding Mendel fails. Just see from a very small lab of Jadavpur University, the AI lab, Sumantra has done this wonderful work, and this is published in IEEE Transactional and Cybernetics in say 2000, I think, 19. So this is Sumantro's details. I do not discuss it now because I cannot finish it. It will be hard for you. So then come to the conclusion. So actually what we discussed, I mean, one approach to actually emotion recognition and emotion control using classical sets, classical fuzzy set theory, means type 1 fuzzy set theory. And we extended it for emotion recognition for using interval type 2 fuzzy set. And we did not discuss the general type 2 fuzzy set, although it is here, because it will be too complex to discuss within this small time. And we can find that interval type 2 fuzzy set can accommodate information of multiple people's opinion. That's why it is more useful than individual person's membership function assignment. So that is the beauty of interval type 2 fuzzy set. But if we use general type 2 fuzzy set, it will be much better. I did not discuss here. General type 2 fuzzy set basically has two different wings. One is called vertical type 2 fuzzy set, which is actually developed at Jadavpur University by our students, two ex-students, I mean, and our faculty, Pratyusha ma'am and myself. And the other group who is working on interval type 2 fuzzy, general type 2 fuzzy set is a group by, and that is actually directed by Professor Hanny Hagras in University of Essex. So they are working on Z slice group. So general type 2 fuzzy set are two different groups. One is vertical slice group that is done primarily at Jadavpur University, and the other one is Z slice group that is done by university, by some people basically at University of Essex. And these two are competitive groups, but both are actually led by, or actually founded by basically Professor Mendel, Jerry Mendel. So there are much more scope to do with those fuzzy sets, but their computation is difficult, but they are much useful when uncertainty cannot be properly measured or cannot be represented by classical fuzzy set only. More is the complexity of uncertainty, and sophisticated is the representation, the better is the result and accuracy. So this is useful for some data like brain data or say image data where much uncertainty is involved. You can use interval type 2 fuzzy set and general type 2 fuzzy set in general. So that's all. I mean, if you have questions, ask me. If you have any questions, you may please discuss. এটা কি ছবিটা বন্ধ করলে বোধহয় দেখতে পাবে স্টুডেন্টগুলো। হলো ভিডিওটা ওদেরগুলো মুখগুলো খুলে দাও, ফেস, they can see. So students, if you have any questions, you may just, yes, anybody can ask questions.
Dear participants, we have Professor Amit Konar with us. So if you have any questions, please feel free to ask sir, because sir has such an expertise in these domains. And sir, thank you so much. Your depth of knowledge and engaging presentation and practical insights have provided us with a new perspective on this critical area. So I would like to request all the dear participants to please ask any such concerns or any such questions to sir.
Somebody has question, right?
Is it
No,
possible
no.
to share the that mathematical proof using that type 2 fuzzy set of your
Yes, yes, yes.
inverse
Actually,
pendulum?
yes, you can get the all the mathematics here. No, this is in Sumantra's paper. I think Anuradha, what you can do. I mean, I
Yes,
mean, I
sir.
can identify some papers that can send you. You can then send it to the students or the
Absolutely,
participants.
sir. It will
Huh?
be very great for participants also.
Okay,
Yes,
okay,
sir.
that is possible. And the basics of the fuzzy sets that can be found, on my computational intelligence book, which is also available online. And so you can get that book, Computational Intelligence Online, that is classical fuzzy sets primarily, and other things covered. But for generalized and interval type 2 fuzzy sets, I mean, we do not have any book right now, but basically, they are available on our papers, and I will share some of the papers with Anuradha ma'am, who will be sharing with you. Okay, the participants. Okay. So Boishali,
Okay, sir.
please
Thank
take
you.
care. You'll be sending the papers to Anuradha ma'am. So Boishali will be doing, so she will be sending by tomorrow. Okay. And anybody have any questions later, you can also ask me later, I mean by email. So Anuradha, you can send me my email, konaramit@yahoo.co.in, so
Yes,
they can
sir.
interact if they have any questions later. Okay.
Absolutely, sir.
Okay. So if any of you have
So,
any question, you may
yes.
ask.
Okay, I think, sir, we can share the paper with the participants first so that they
Mm.
can, go through the all the details and all these
Mhm.
exciting works which we have, done under your supervision in
Mm.
Artificial Intelligence Lab of the Jadavpur University, so that they can be, excited to collaborate or to find some guidance from you, sir. So it will be
Okay.
great. And dear participants, I'm just requesting you to just switch on your camera then, so that we can take an attendance for this session for 2 to 3 minutes. Sir, I would request you to just stay with us for 2 to 3 minutes, sir.
Okay, thank you. Mm.
Sir, can you recognize
So,
me, sir?
yes, yes, I can see many of you. No, Archana, I can see, I can recognize. I can also recognize you. Yes, I can recognize many people. Yes.
So it's the
Good evening, sir.
Good
Good to
evening.
see you.
Yes. Yes, thank you.
Good evening, sir.
Good evening
evening,
to
sir.
everybody.
শুনতে
Yes.
পাচ্ছেন?
হ্যাঁ, হ্যাঁ, শুনতে পাচ্ছি। হ্যাঁ। সবাই ফেসটা বোঝা যাচ্ছে না, একটু আবছা হয়ে গেছে। সো মানে ব্লাড হয়ে গেছে একটু একটু বলে বোঝা যাচ্ছে না। কয়েকজনকে চেনা যাচ্ছে আর কি। অর্চনাকে খুব ভালো চেনা যাচ্ছে। সবাইগুলো বোঝা যাচ্ছে না আর কি। ঠিক আছে।
Okay, thank you so much, participants. So you can switch off your camera right now.
So we will start within next 3-4 minutes.
Yes, sir. Yes, sir. Because dear participants, it is time to take
Just
a
say
short
now it
break.
is 7
It's 7:32,
35,
sir. Yes.
7:38, 3 minutes.
Yes, yes,
Okay.
sir, sir.
Okay.
So we will be back at 7:38 p.m. So you just take a short break, and we are going to process this session, and then we will be back in the next session with sir only. Yes,
Okay.
sir.
Thank
Thank you
you.
so much, sir.
Thank you, Anuradha. Okay. একটু বন্ধ রাখো, অডিওটা বন্ধ রাখো।